Welcome everybody to this new ANEMEL webinar. Today we have one of the ANEMEL doctoral candidates based in EPFL in Switzerland. She's been working on platinum-free catalysts for a while now and recently published two very interesting papers. You can read more about them on the anemel.eu webpage and the blog. We've got articles on both papers explaining the technology and how both of them broke records in water electrolysis, which is pretty nice. ANEMEL, I think we've said in all the webinars, but ANEMEL is a project funded by the European Innovation Council. And these webinars are part of the dissemination and communication activities that we carry out to, engage the audience and, so everybody can learn a bit more about the world of hydrogen and the world of seawater electrolysis. So today we have Ariana Serban from EPFL. Like I said, she's been working on her doctoral thesis in EPFL in Switzerland for the past few years. Most of that has been working for ANEMEL, and she's got some very exciting results to share. She's going to tell us all about the latest papers. And if there's any questions throughout the presentation, we'll take them at the end. Please put them in the chat on YouTube and we'll read them afterwards and address them to Ariana. And without further ado, I think, Ariana, the floor is yours.
Thank you very much. So, hello everyone. Today I will present part of my work and I will start with non-PGM. PGM comes from platinum group metal, cathode for high current density water splitting. So I'm from EPFL, from the lab of anorganic synthesis and catalysis, and my supervisor is Professor Shilehu. Thank you very much for this opportunity. So this is our present and this is how our life looks like. It's very exciting. We have a lot of industry and the main building blocks, I would say, would be the stainless steel, ammonia synthesis, ceramics and glass, and of course now we have also AI. But what are these building blocks having in common? And the answer is very simple. We use fossil fuels. So what's about fossil fuels? Okay, so we accumulated in a lot of years an unknown amount of tons of fossil fuels. And in the last 300 years, actually, we consumed around 1 trillion ton of fossil fuels. And what do we know? It's that in about 50 years, we will consume the rest of it. So the estimated amount of fossil fuels is around 0.75 trillion tons of it. Okay, so we are out of fossil fuels. What do we have to do? I would say let's think about renewable energy sources. And here hydrogen plays an important role. So here we have the wind, we have the water, which is plenty of it, and also hydrogen is a great way to go. How to obtain hydrogen? Here we have one type, and it's called water electrolysis. And at low temperatures, we have the first water electrolysis, a very well-known technology. It's alkaline electrolysis, which is a membrane-free. So basically here we have a diaphragm that from the cathode, the OH passes, so the ions passes to the anode. But the advantage is that it's a mature technology, but unfortunately the efficiency is low and also it has a lot of losses because of this space in between cathode and anode. Here the reactions are happening. At the anode we have the oxygen evolution reaction, at the cathode we have the hydrogen evolution reaction. So scientists actually came with a new idea, having a polymer electrolyte membrane. What does it mean? It means that we have a membrane in between the anode and the cathode. So we don't have so much space in between these components where the reaction happened. The PEM, water electrolysis, comes from proton exchange membrane water electrolysis. So from the anode, the protons are going to the cathode. Okay, so here we have some advantages. It's quite an efficient option, but unfortunately it's using the PGM catalyst, so the platinum group metals, which are very expensive, and also they're not so much on the earth. To combine both advantages, alkaline but also this PEM water electrolysis, scientists came with the third generation. And here we have the anionic exchange membrane water electrolysis. Here from the cathode, the OH, so the anions, are transported to the anode, and the reaction is happening at the anode, oxygen evolution reaction, and cathode. Here the technology is still under development, but we need PGM-free catalysts to improve the technology. And here we play a role. And my work will be just focused on AGR, so hydrogen evolution reaction side, so just like the cathode. Going further, what we wanted to do is to develop self-supported catalysts for hydrogen evolution reaction. And what do I mean by self-supported? Here we have some commercial available supports like nickel mesh support, and you can see how it looks like, and carbon paper support. What we are doing is using one-step electrodeposition from a bath that is containing nickel and molybdenum. And you see the supports, how they are looking. They have the catalyst on it directly grown to have a better adhesion and also better activity. And if you're not familiar with electrodeposition, actually it's quite famous because a lot of pieces of like metal pieces from boats, watches, a lot of devices, they are doing electroplating. This is an industrial process. Here how the baths are looking like. And yeah, so basically the main idea is to apply a current, and see here like in a bath you have two pieces and then they will cover each other. This is a well-known process, and this electroplating bath, it's called the Watts electroplating bath. It's well known, and here the core of it is the boric acid, which is a buffer. Another well-known kind of electrodeposition made in the lab this time is having a reference electrode, so we don't have just like a counter and a working like previously. And the bath, actually the main core here is like the citric acid, which is a complexing agent. In our case, we are not using this kind of baths. This is why we are comparing to it to see how our electrodeposition bath and our catalyst, it's better or worse than this electroplating well-known baths. Okay, aim of this work to develop robust AGR, hydrogen evolution reaction catalysts for high current density. Assess AGR activity in a 3-electrode setup. This is lab-based setup. I will explain it. Compare our electrodeposition bath with other well-studied ones, as I told you before, the boric and the citric, and also the state-of-the-art, the platinum, so the PGM, actually, AGR catalyst. And here we have a linear sweep voltammetry. And what is important, what we are interested is to see on this axis highest value, and in this case it's with our catalyst, then it is followed by the citric, boric, platinum mesh, nickel mesh. And also one important parameter is that we want to see this line as close as possible towards zero. Okay, so in this case, it's worth it. This is the catalyst grown on the nickel mesh, and we compare it also with the platinum mesh. Going for the carbon paper, because we started with two supports. Here we have again the catalyst that we have done, and we compare with the one that is deposited from the citric bath, boric, and also platinum on carbon, but this is sprayed. So this is usually what people are publishing as the benchmark. And here we have, again, we have here the line is closer to 0, which is amazing. Also, it doesn't reach as high current densities as here, but still it's manageable. Okay, so this was just in a 3 electrode setup configuration lab base. Now we wanted to integrate the catalyst into the membrane electrode assembly, so the device itself, the core of this project. And here I will show you this movie to give you a little bit of an idea what does it mean. And here it's an water it's an electrolyzer device. So here we have the end plates. Here it's called a current collector. Here we have the flow channels, and let's go to the assembly. So here we have the flow channels. We have the first catalyst, a gasket, the membrane, again the gasket, catalyst, flow channels, current collectors. In our case, we have just like the anode flow, and here we have a dry cathode, we have the heating cartridges, and this is the operating device. Okay, state of the art would be with the anode, that is nickel iron, cathode nickel iron cobalt. We have a commercial available membrane which is called Sustanian. They use 1 molar KOH at 60 degrees and the cell voltage at 1 amp, while doing electrolysis it's 1.9 volts. And here I will show you an IV curve. Basically, it's a transient method. Basically, you are like sweeping the voltage to a certain point and you will see the current density. In our case, we see that the catalyst we developed, it's the best one, compared also to platinum, citric, boric. But here it's a short time measurement. What we need for real application is the electrolysis itself. And here we applied 1 amp per square centimeter for more than 100 hours. So here it's roughly 150 hours. And what we have seen is that we have a stable electrolysis compared to the one of platinum, that we see here degradation, mainly to the bubble effect. So basically bubbles are created and they're just like detaching the sprayed catalyst from the substrate. We want further to do some electrolysis, but even in higher current densities, usually people, they are just keeping 1 amp per square centimeter, 0.5, 3, 5 amps, 10 amps. It's not so used nowadays. Here we see again a stable behavior. So at 3 amps, it would be around 2 volts. As well, here platinum has some fluctuations, basically because of the bubble effect. And in order to compare this work, I would say this is where we are going. And as said previously, people that they just like go for 0.5 amps per square centimeter or 1. We also try to use different supports, and here we have a nickel foam support with the catalyst. This is how it's looking like. And also we had a nickel paper support. This is how it's looking with the catalyst. We have done the electrolysis as well. We have this part where we call it activation of the catalyst. So basically the voltage, it's dropping, and I'll explain it a little bit later. And then we have a stable curve with a little bit of degradation over 100 hours. Going for the nickel paper, we have also this process of activation, and then we have a stable behavior at 1 amp at 1.76 volts, which is very good. Okay, so here, as I told you, we had activation or reconstruction of the catalyst. And we have done the selected area electron diffraction using a TM. And you see here, as prepared, we have a morphology, a nanosheet morphology. And after activation, so after putting 1 amp per square centimeter, the morphology is completely changed. And also we can see this by the selected area electron diffraction, and I will show you briefly. I hope. Okay, so wait. Here is as prepared and see from more particles, and this is after activation. So you can see in parallel that their structure has changed. Okay, in order to see actually what's the relationship in between of the structure activity, we have done operando measurements. And here I will start with the citric nickel molybdenum, and we see that here we have a nickel 4 molybdenum. Okay, nice. That it doesn't change under continuous operation. So we are starting from the dry state of the catalyst to the open circuit voltage. This is why like OCB is coming from, and then during this activation. In our case, what we observe is that we are starting from a nickel 4 molybdenum, which is tetragonal, and by going through this operation process, we see these two diffraction lines that are appearing. And these two diffraction lines indicate a D1A superlattice of this alloy. Going further, we have done also XIS to see how the surface is behaving, and here we can see that just applying the activation process, nickel is quite, I would say, a little bit below zero. This is just because molybdenum is giving him electrons, and then just like by applying it's going to zero. So the activation is used to reduce the surface oxides, because nickel and also molybdenum, they are oxophilic, so they love oxygen. In the case of molybdenum, we are starting from this, so it's intermediate state in between 0 and 3. And by going with this activation process, you see that this peak is moving towards metallic molybdenum, but it's not overlapping with it, so we still have some oxidic species. And what we have here is a nickel 4 molybdenum alloy with an molybdenum oxide. One it's helping the water, like the dissociation, and the other one the hydrogen absorption. This catalyst was also implied in this work. It's called pure water electrolysis using platinum group metal-free electrocatalyst. And here we have an anode, which is nickel iron. We have the cathode that I've presented. So basically in pure water, what they are using, they're coating it with an ionomer to help the OH transport and also the conductivity. Here as well, the results are very, very well. And here we have an electrolysis of around 600 hours at 1.8, which again proves the stability and also the efficiency of this catalyst, even in pure water electrolysis. As a conclusion, we have the first one. We developed an, I would say, innovative, easygoing catalyst with remarkable activity in both alkaline and pure water. It has promising performance for the anionic exchange membrane water electrolysis, comparable to the expensive platinum-based system. What we found out is that the cathode serves as the primary bottleneck in pure water. Therefore, ionomer coating on both anode and cathode is crucial for achieving high performance pure water electrolysis. And last, we have done operando each side of the catalyst structure to see the active form, and we discovered that it's an unconventional nickel 4 molybdenum alloy with surface molybdenum oxidic species. So thank you very much. This is my supervisor and my colleagues as well. Thank you. That's everything from my side.
So thank you so much, Ariana, for the super nice presentation. I like, how very clear it was. And obviously I love the emojis at the end. I think that's a fantastic way to conclude the presentation. I had a few questions from my side. While we get the questions from the audience, if anybody is watching and has some questions for Ariana, please address them in the YouTube chat and we'll pass them on. In the meantime, so I've got one question specific to the high current densities that we're talking about. Because for people outside the lab and the electrolysis world, this term may sound a bit weird. So I wanted to understand, why is it that most people use very low current densities to test the devices? And what's the implication of going higher into big current densities like you did in both papers? Um, I guess this has some important industrial implications, but I wanted to understand better why we need to reach better limits in terms of current densities. And then as well, if you could talk about the other paper you recently published, where we basically maintain a very high current density during a very long period of time, and why that is very important for the state of the art.
Okay, so I don't know, should I close the screen sharing? Should I keep it
It's
on?
fine. People won't be able to see, just if we do the questions, they're only seeing ourselves, so it's fine. If
Okay,
you
perfect.
prefer to close it, that's fine.
Okay, perfect. I will just close it because it's very weird. I just see. Okay, stop sharing. And now let's go here. Okay, so about the current density. Usually people are just using the 3 electrode setup. So it's a lab base. You will have a beaker and you have 3 electrodes. This is not the real device. And this will not actually convert what we see in 3 electrodes into the system as well, because it's different. When you have the system, you don't have just like, 3 things in a beaker. You will have a complex where you have a membrane, will have contact in between, you have gasketing, you have flows, you have heating, and so on. This, I would say, people just report mainly in beakers, and usually they put 100 milliamps. When you are going further, let's see, industrial relevant, I would say it's 1 amp, starting from 1 amp to higher. When you are doing this, a lot of I would say, if your system is not stable, you will see degradation in time. By increasing the current, your materials will degrade faster. And imagine, because you are just like splitting more water molecules, therefore you have more gases, and then you have a diffusion limited process, because you will have so many bubbles that actually they don't have time to escape from there. And also it will be a problem with the interface, because you have bubbles in between your catalyst and also the membrane. So yeah, going for very high current densities, it's usually to test the robustness, and also to see how fast the degradation of your system is. Basically, you are stressing out, especially what we have done when we applied 10 amps per square centimeter, was just like to stress out the membrane and also the catalyst, and to see how durable they are, even in very, I would say, unrealistic conditions, because you don't want it will be all the time, I would say, a compromise, and you want stability a long time, because you don't want to change every time. And here we are talking about the cell, but we are not talking about the stack. You don't want to change every, I don't know, maybe 4 or 5 or 6 or 10 days, your catalyst, your membrane. Then you have to flush everything with the electrolyte, then coming back, then operating, then blah blah. You don't want that. So you want a very long operation of the electrolyzer. But yeah, I hope I
Mhm.
answered.
Yeah, so it's basically like when you go to IKEA and they show you all these machines they've got to test a mattress over time.
Exactly.
It's basically stressing the electrolyzer as much as you can during as much time as you can to
Yes.
see if it can actually withstand industrial conditions, which was sort of the big question: can we scale this up to industrial conditions further along? I had another question before we go to the ones we just got from the audience, which was related to ANEMEL, because ANEMEL is an international project that involves people all across Europe, in obviously in Switzerland where you are based, but also in Slovenia, in Ireland, in Spain. How has this project sort of influenced and benefited the research that you do in EPFL towards putting together very nice electrolyzers and possibly soon enough the stacks and the machines that are gonna do seawater electrolysis?
So basically, I'm very grateful to ANEMEL because I don't know if people they know there, but we have a lot of work packages. And along with these work packages, we have different expertise. So there are people in work package one, my work package, that are doing the AGR catalyst, my case, and also the oxygen evolution reaction catalyst. Then we have the work package two, where we have the membrane, where we have then we have the work package three, where we have the assembly itself. What I mean, we have until 7, and also here is the communication and dissemination and so on. Basically, it's a big teamwork, and it's really nice to have a lot of people with different backgrounds talking and also supporting each other, communicating, presenting, putting a lot of questions. Sometimes, also when we have our meetings, it can be very challenging because everyone is very curious. And some people also I mean, they're just like, I'm sorry, I need to do this and so on, for example, for you guys. And it's just like, it's a big team and everyone is concerned to doing like its job perfectly, but then to make the whole stuff, just like um, together. So yeah, it helped me a lot because I had a lot of discussions with people that they had more experience with stacks, with more engineering. Um, and yeah, we just like, I would say we just learn from each other, which is the most important part.
Yeah, that is a very nice appreciation, and thank you for including the communication team there, because I think a lot of people forget that it's part of the project as well, and actually it was very interesting to work together, to produce the blog posts on your papers, which again are available on the project's webpage, anemel.eu, if you want to read more about them. And now we've got questions from the audience. I'm gonna try to read them out directly from YouTube, which is a little bit challenging, but here we go. So we've got the way more specific than the ones from me, because obviously they come from experts in the
Okay.
topic. But they're asking, so we've got someone called Michael asking about the research gaps in the electroplating of molybdenum and nickel for water electrolysis of molybdenum and nickel. He's asking about both alkaline and acidic conditions, but I'm assuming in this case, we're probably better equipped to answer about the alkaline. But yeah, what are the research gaps in electroplating with abundant metals, and what are the degradation mechanisms that could, you know, hinder the development of this type of catalysts?
So I will start with the degradation. I don't know about the acidic. I will just talk about the alkaline because I have done the studies. So I was concerned because in literature there are a lot of molybdenum dissolution in water electrolysis. In my case, I also see some dissolution of the molybdenum after 100 hours. So how you are measuring it more precisely, I'm doing ICP-MS, taking the solution and go to do the quantitative analysis, how much leaching of the molybdenum is in the solution. And I see um, some, I don't remember exactly the number, but it was just like parts per billion, so it wasn't a lot, at least after 150 hours. Now, if we are doing in 1,000, 2,000 hours, I would not actually be able to say. I'm because I've never tested in like such long times. So this is for the stability. And the second, you told me about the electroplating. Uh,
So they're asking about degradation and about any gaps in the research for electroplating in molybdenum and nickel catalysts. If there's anything that's sort of hindering the progress in the field of non-PGM catalysts.
I mean, with the electroplating, people usually they are doing with this boric acid, citric acid, sulfamates. After doing the electroplating process, they are also doing hydrothermal. Um, to like build a lot of configuration about like of electrodes, self-supported electrodes. I'm not talking about powders, because we are going to another category of catalysts, and it's not fair to compare them. I would say also electroplating is quite used if I'm thinking about the last years in big journals, all the special configurations. I think one of three they were using electrodeposition with a lot of like different baths, and not just constricting ourselves to nickel molybdenum. You can have also cobalt, you can have also iron, etc. You can also alloy actually nickel with platinum.
Thank you for the answer. I think you were spot on. But if there's any follow up, again, Michael, feel free to use the chat. We have another question from someone called Antonio, who thanks you for the presentation and then asks about ionomers, in particular whether we're using them in electrolysis, which I think could refer back to your chat about the work packages and how different teams do different things. But yeah, if you've got any updates on the use of ionomers in the configuration for electrolysis and the cells and the stacks.
Yes, so basically, and this is also my next work, I would say. So they just pointed out very nice. Ionomers, they play a really important role. I'm not. It's just a really. It has to be a really good synergy in between the membrane, the molecular weight of the membrane, which is very important, all the properties of it, the thickness, and the electrodes. And here it's very important, especially in the self-supported, what kind of substrates you are using. For example, in the case of nickel foam that I've used, I've seen a little bit worse results because of the contact, interfacial contact. So it's like the foam, it doesn't, just like um, stick exactly like a paper, for example. Also here, it's like the porosity and so on is very important of the substrates. With ionomers, um, the state I would say which is like very known is the Sustanian XA90. Then we have the Piper ion. Um, Now what we are using in the lab is something that so the membrane it's called BPTP, phenyl triphenolo something. I'm sorry, I'm not like an expert in membranes. The ionomers, we have quite a lot synthesized in our lab, and also what we have from ANEMEL. It matters, like the amount of the ionomer that we are coating matters, because we see differences. If we are putting more ionomer, actually it's blocking the catalytic active sites of the catalyst. So I don't know, I can talk a lot about it, but I don't know if I
I
replied.
think I could we could redirect people to the ANEMEL webpage, and there's a few articles on membranes, and there's gonna be more coming up. And actually we want to talk about membranes in one of our upcoming webinars with our partner ACFA in Belgium. So maybe they can talk a little bit more about the advances in ionomers and the different ingredients that we're using in membranes, which we are trying to do the same way we're doing catalysts with no CRMs and no platinum. We're trying to do membranes and any plastic components without PFAS to remove the fluorinated chemicals from there, which again has been covered on the blog if you want to go and check that out. We have another follow-up question by Michael. And then some other user thanking you for your presentation. Apparently found us randomly on YouTube, which I didn't know could happen. And we've got like almost 50 people watching live, which is really cool, honestly, for a webinar like this. So apparently YouTube this is some sort of trending thing on YouTube now, and it's being recommended to users that did not follow the
This is
channel. And that's very cool. So Michael is saying, um, is asking about the post treatment that you do after the electro deposition of the molybdenum nickel. Like, do you do any annealing or any activation after creating the surface? It's
No,
just like you soak
no,
them and they're ready to
no,
go.
no, that's the point. So, in my first 6 months of my PhD, I tried to do this stuff and it was so long. And one synthesis was just like around 2 days. And then, like, just like trials and blah, blah. And I discovered this, which actually I made one electrode in 1000 seconds. So it's really fast. And when I discovered that I can do the electrode and put, I don't know, 3, 4 cells in the same time and do, I don't know, maybe 3, 4, 5, 6 catalysts in one day, I was like, this is the best. This is just like wonderful to have it in such a short time and just like go directly in the device or in the beaker. So no post treatment. Just this
Which
activation step, but this is an in situ process where you apply current and the surface will reconstruct by itself and will reduce oxides and like they will just like have a better performance. But that's it.
I think it's promising in terms of scalability and going to industrial levels, because if we don't require a complicated setup to produce the electrodes, and then we're using molybdenum and nickel, which are not as expensive as other alternatives, like we're talking about platinum or palladium before. This is cool because then you can just have the whole soaking method for the electroplating. And then it's just like a couple of steps. You said 1000 seconds. My math is very bad, but that sounds like a really quick process to produce the catalyst. So you can, scale that up to industrial levels very quickly. That's
Yeah.
really cool. So what could be the sort of next steps in terms of, I know you're probably thinking about the end of the PhD and the end of the project, not thinking about the next steps of these catalysts, but what do you think could be the next steps in terms of, do we find new materials? Do we use the materials we have and then just scale them up and try to figure out how to make this industrially? Um, is there any other parts of the electrolyzer or the stack that may need a little bit more improvement before we try it? Or are you confident that, we're gonna have a demo at the end of the project that is gonna showcase seawater electrolysis, or like, dirty water electrolysis in a very efficient way?
So here I don't agree with you. I'm not looking forward to finish my PhD. And yes, I took into consideration scaling up this process and also finding some other um, viable catalyst. A disadvantage with this catalyst, especially in scaling up processes, would be the chlorine evolution reaction. So what I see is when I'm electrodepositing, my electrodeposition bath contains ammonium chloride. And when I'm applying this, it's like a huge current densities to do this catalyst, I see a lot of chlorine evolution reaction. Here would be just a very challenging because it's very toxic for human beings and you need huge fume hoods. Therefore, what I came up is to replace this ammonium chloride. And in my final report for the ANEMEL, I described how this ammonium chloride can be replaced by some other ammonium salts. Therefore, we have also other viable solutions in case we want to scale it like up and to diminish like as much as possible the risk. It's true that the performance is not as good as this catalyst, but it's still um, like in our like lines, I would say performance lines. Scaling up, we also starting to do it at the moment. We send some samples to our collaborators from Berlin and also from Ireland, 5 by 5. In order to do bigger, I would say we need some industrial partners that they have more expertise because this is not a linear process. It's not like, okay, so I'm doing this at 1 square centimeter and then it will just like be the same at 2 and so on. If we want 100 by 100, the game will change drastically. But I am quite confident that at the end of this process, of this project, sorry, we will be able to deliver a good prototype. And a good prototype
Mhm.
also from the anode, cathode, membrane, ionomers, and so on. And also the
Yeah,
system itself. because the
And
system is so.
hopefully, I think we still have maybe, I mean, not a couple of years, but like 18 months to go till the end of the project. So that means that our industrial partners, which include the NORA in Italy and ACFA in Belgium, among others, they could sort of try to develop these last steps to see if we can scale up to bigger sizes. And then we'll probably talk about this in different channels and then further down the line. But we got some new funding by the European Commission and the Clean Hydrogen Partnership to follow up on the results by ANEMEL to scale the project up and see if we can reach higher TRLs and higher industrial applications. We'll tell you more about this project as soon as we're ready to talk about it. But it's really cool that it's the results from ANEMEL in the lab scale are proving successful. Of course, like you said, chlorine is complicated to deal with, and it's very not only very toxic but also very corrosive, which is going to be a mess for the metals and the instruments that we're going to use. But we can probably deal with it and find ways to deal with it to make sure that we sort of have selective electrolysis towards water splitting and the production of hydrogen. I
For
don't
this
know if you
catalyst, sorry for interrupting.
yeah,
So
go
for
ahead.
this catalyst, with the because I used ammonium chloride, so to avoid, I found another three salts that actually they're working quite fine. So we have another three options in case something it's not going well. And yeah, you're right. It's
Just
very
don't tell us what it is in case we need to publish or patent before.
okay.
But yeah, that's very good news, and it's always great to have like a preview of the results here on the webinars before we see them publicly. Again, unless you've got anything else, I think I'm very happy to close the webinar now. We've got no more questions from the audience, who, by the way, have been very participative, sending ideas and sending questions, and I really appreciate that. Thank you again, Ariana, for your contribution, for your talk, and for your knowledge answering all the questions. I'll see you in Ireland in a few weeks. Everyone in the ANEMEL meeting, the ANEMEL consortium is gonna meet in Galway in Ireland in a few weeks to sort of update each other on the progress of the project and share results and work together. So looking forward to seeing you there. Thank you again for the presentation and organizing the webinar. And for everybody else, thank you for joining us on YouTube today. This is gonna stay up, so if you want to check it out later, it's gonna stay here for a very long time, at least through the duration of the project. I encourage you to visit the webpage that we have, anemel.eu. It's ANEMEL, which is hard to spell, but that's the webpage for the project. We've got a lot of blog posts and information about the project, infographics, videos, if you're interested in learning more about green hydrogen and seawater electrolysis. And then if you want to stay updated about the upcoming webinars, which will follow up with more information on ionomers and membranes and the rest of the parts of the electrolyzer, you can subscribe to the ANEMEL newsletter, and we're going to send you a periodic email every couple of months with information about the project, and then, of course, information about the webinars, which will keep coming up every, I don't know, ideally every couple of months. So yeah, stay tuned. Thank you for joining, and yeah, see you very soon.